Hi guys, welcome back to chemistry. In this video, we are going to be working on balancing chemical equations. We're going to be doing equations that are maybe a bit more complicated than the ones we did in my last chem video. So I highly recommend you go back and watch the last one I uploaded before this one if you haven't already, just to make sure you have a really good sense of what chemical reactions are, what the process is like, and then how to properly balance an equation like this one. We've had a few of the simple ones we did in the last problem. They ended up being not too bad. The ones we're going to be doing in this video are going to be maybe a bit more complicated. So let's get started. Just as a quick reminder of what it means to balance a chemical equation, it means to alter the coefficients so that we have the same number of atoms on the left side of the equation as we do on the right. So what I like to do is I like to start with a list of everything we have on the left and on the right. So let's take a look. On the left side, it looks like we have, here, let's go over everything first. So we have lead reacting with the water molecule, reacting with the dioxygen molecule, and they produce lead to carbon. No, sorry, it's not lead to carbonide. This is lead to hydroxide. They react together to form one product of lead to hydroxide. And this is what we call a synthesis reaction. Lead, water, dioxygen, and then lead to hydroxide is what forms. So I want to just make a list of everything we have on both sides of the equation together. It will just give us a good idea of what we have to do. So I'm going to see how many leads we have first. We have just one lead atom. How many hydrogens do we have? Well, this little 2 means we have 2 of those hydrogen atoms. And the oxygen, we have 1 over here in our second reactant, and then we have 2 oxygen atoms in our third reactant. So we have a total of 3 oxygen atoms. All right, now I want to do the exact same thing on the other side of the equation. So on this one, we have 1 lead atom. We have, whenever we have a 2 outside of parentheses like this, inside parentheses, we have a polyatomic ion. So whenever we have a subscript outside of a polyatomic ion like this one, it means that we are going to be distributing it to both of the atoms within this ion. So the 2 gets distributed to the oxygen, and then it also gets distributed to the hydrogen. Everything in the ion gets affected by the subscript. So we have, in this case, we can tell that we would have 2 hydrogen atoms. And then how many oxygens? Well, we're also going to have 2 oxygen atoms. So now we have a complete list of what we have on both sides of our equation. Now let's go ahead and start comparing everything. So it looks like our leads are already balanced. We have an atom on each side of lead. Same thing with hydrogen. We have 2 hydrogen atoms on each side, so we know that hydrogen is balanced pretty well. The only thing we have left to worry about would be the oxygens. We have 3 oxygens on the left, and we only have 2 on the right. So in this case, we might want to make the number of hydrogens on the left side even, because it just makes things so much easier to work with overall if we have even coefficients, even number of atoms. So I want to see if we can alter this in such a way so that we can make the number of oxygens equal on both sides. This is where things get kind of mathy, for lack of a better word. Things get kind of algebraic. We have to think in terms of factors, in terms of multiples, in order to decide what the coefficients should be to make this balance. What I want to do is I want to find the LCM, the least common multiple, of the number of hydrogens on the left, which is 3. Sorry, I meant to say oxygen. The number of oxygens on the left, which is 3, and then the number of oxygens on the right, which is 2. So the least common multiple of 3 and 2 would be 6. So I want to make the number of oxygens 6 on both sides. How do we accomplish that? Well, not like that, apparently. I'm not good with this thing. I've been using Zoom for over a year, and I still am pretty bad at it. I apologize. How embarrassing. So I want to multiply whatever is needed to get 6 oxygens on the left, and then multiply whatever is needed to get 6 oxygens on the right. So let's go to the left. We have 1 oxygen, 2 oxygens, so we have a total of 3. But what if we were just to double this water molecule? Let's see what happens if we were to just do that, if we were to double this water right here. So in water, we have dihydrogen and we have oxygen. So they would both be affected by this coefficient. We're doubling the molecule. We have twice as many hydrogens as before. We have twice as many oxygens as before in this particular reactant. So let's do a recount. How many oxygens do we have now? So we have 2 oxygens right here. Oh, yeah, we have 2 oxygens here and then 2 oxygens right here as well. We have 4 so far. We're trying to get 6, so we're going to need to modify this in such a way so that we have 6 oxygens instead of just 4. This is where you kind of have to be strategic in understanding how exactly to get there. We want to understand which of these we want to modify. Do we want to modify the water, or do we want to modify the dioxygen? I think we want to modify the dioxygen, because if you can modify just one thing without affecting everything else, you should definitely do that. For example, what I mean by that is, if we change this 2 coefficient right there, we're going to have to rebalance hydrogen. If we put a 2 right here, we don't have to rebalance anything at all, because oxygen is the only atom being affected by this coefficient, which makes things really convenient, really easy to work with. Life's good. So let's do a recount. So now we have 2 oxygens, and then this would be 4 oxygens. We always multiply the coefficient by the subscript by whatever the atom in question happens to be. In this case, it's oxygen. So we have 6 oxygens altogether on the left. I want to just update the counts as I go. Now let's see if we can do something similar on the right side to make sure we have also 6 oxygens on the right. So at the moment we can tell we have 2. We want to think about what this coefficient should be out front in order to have a total of 6 oxygen atoms on the right. So 2 times what number is 6? That would be 3, of course. So we're going to multiply the entire we want to multiply the entire lead-2 hydroxide atom, or lead-2 hydroxide molecule, is what I meant to say, by 3. So now let's do a recount of everything on the left after we make that modification. So we no longer have just 1 lead atom. We have 3 lead atoms now. We have 2 times 3 is 6, so we have 6 oxygen atoms. And we also have 6 hydrogen atoms. Now let's do a quick comparison, see what we have now. So it looks like the oxygens are balanced. We just have to balance the lead and also balance the hydrogen now. So we have 6 hydrogens on the right. We only have 2 on the left. So that means we're going to need to take the number of hydrogens and multiply that by 3 in order to get 6 hydrogens on the left side, in order to make the hydrogens balanced. So we already have a 2 there, and I want to give it an additional 3. 2 times 3 is 6, so I'm going to make this coefficient. Whoa, I didn't mean to do that. I never will learn. Here, let's just do this. We're going to have a coefficient now of 6. I keep telling myself I'll get the hang of this one day, but I don't think that day will ever come. I think I'm just predestined to suck at using Zoom. So now let's go ahead and do a recount. So let's see how many oxygens we have. So oxygens are going to be 6 plus the 4 we have in our very last reactant. So we have a total of 10 oxygens now. Now let's take a look at the hydrogen. Hydrogen, it looks like we have 6 times 2, we have 12 hydrogens this time. And then the lead is unchanged by all of this. Now let's go ahead and do the same thing on the other side. Figure out what modifications we need to make in order to make this thing balance. So we have 12 hydrogens on the left. We have 6 hydrogens on the right. So what I want to do is I want to double everything on the right, just so we can have a balanced number of hydrogens. So instead of this coefficient being 3, I'm going to make this coefficient into a 6, because just like we did in the last one, I'm going to multiply this 3 by yet another coefficient to produce a new coefficient. This time it will be 6. If my computer will let me, there we go. Sometimes I have to threaten to throw my computer out the window for it to start working. I'm glad I don't have to resort to threats this time, but the video's not over yet. I might still have to later on. So what was I saying? We had 3 before. I'm going to double the 3 to get us a total of 6 atoms, or 6 molecules of lead-2 hydroxide. So now let's just go ahead and update our count real quick. So we have 6 lead atoms. We have, this would be 12 hydrogen atoms. And now what about the oxygen? We have, this would be 6 times 2 gets us 12. So we have 12 oxygen atoms. So let's do a comparison real quick. The hydrogens are perfectly balanced. The leads still need to be balanced. I'm going to leave the leads for the very end. And the reason why I want to do that is because we can modify this lead. We can modify I can't talk today. we can modify the coefficient in front of lead without affecting anything else. So whenever we have a situation like that, it's always good to save it at the end. That way you don't have to constantly rebalance a bunch of things. So now let's focus on oxygen. We have 10 oxygens on the left. We have 12 oxygens on the right. So we want to think of a clever strategic way in order to add an additional 2 oxygens. So for the same reason why we leave this lead for the very last step, we want to modify this one instead of modify that one. Because if we modify oxygen here by changing the coefficient, we would modify hydrogen yet again, and it would kind of screw everything up. We'd have to go rebalance hydrogen yet again. This is kind of like solving a Rubik's Cube. It's kind of fun, isn't it? Kind of like a puzzle. I don't know if I'm just a really weird guy for thinking that, but I think it's kind of fun. It's like a puzzle. If only balancing my checkbook would be this interesting. You know, I'd have not many money problems if that were the case. Wishful thinking there. So I don't want to modify the water molecule. I actually just want to modify this the dioxygen. So what I think we could do is double this entire molecule right here. So that means instead of having a coefficient of 2, we would have a coefficient of 4. And let's just go ahead and do a recount to make sure we have what we want. So we only affected the oxygen, so I'm only going to recount the oxygen on the left. We have 6 oxygens, and then 4 times 2 is 8. So we have 6 oxygens plus 8 oxygens. We get a total of 14 oxygens. So that didn't work out really well, because if we count the oxygens we have on the left after we modify the coefficient, we now have 6 plus 8, so we have a total of 14. We're only trying to get 12, which means that 4 may not be the best choice of coefficient for the dioxygen. So I want to modify that. It was 2 before, that wasn't enough. It's 4 now, and 4 is a bit too much, so I'm going to take the middle road and pick 3 to be this coefficient, and then do a recount. So let's count everything. We have 6 oxygens plus 6 oxygens on the left. So we have a total of 12 oxygens now. And now I want to do the same thing on the right. Well, actually, we didn't balance anything on the right recently. We only have been focusing on the left. So the hydrogens and the oxygens are now perfectly in balance. We're almost done. Just one more step we have to do, and it's the easiest step of all. We just have to modify our lead atom to make sure we have the same coefficient as we do on the right. So we have 6 leads on the right. That means all we need to do is slap a 6 in front of this lead atom in order to properly balance the entire equation. Update the count real quick. So it looks like we're done, but we're not quite finished yet. We have to reduce this. I don't know if you remember the last video, what we did to simplify something like this. I used a fraction analogy. I said that in the same way we have to reduce a fraction, 2/4 reduces to 1/2. This isn't considered complete. 1/2 is considered complete. So a similar situation applies when we're balancing equations. We want to take all of our coefficients and then divide them by the greatest common factor of all of them. So we have a 6, we have a 6, we have a 3, and we have a 6. So the greatest common factor, the GCF of 3 and 6 would be 3. So I'm going to go ahead and divide all 4 of our coefficients by the GCF. I'm going to divide all 4 of them by 3. And when we do that, we actually get 3 lead atoms. We get 3 water molecules. This is going to turn into 1 O2 molecule. And then we're going to have 3 molecules of lead 2 hydroxide. Let's see if I can do this without messing up. I don't like my chances, to be honest with you. Come on. There we go. So we're going to have 2 lead atoms, 2 water molecules, 1 O2 molecule, and we're going to have 2 lead 2 hydroxide molecules. Life is good. Everything is perfectly in balance. All right, so we have a new problem to work on this time. We have another chemical equation to balance. So this time this is another synthesis reaction, similar to the one we had before. We have a molecule of scandium oxide reacting with a molecule of sulfur trioxide, and they form a product. This would be just one molecule of scandium sulfate. And again, it's a synthesis reaction, and we want to get to work on balancing this thing. So I want to do just like we did before. I'm going to start off with a list of everything we have. So it looks like we have, on the left side, we have 2 molecules of scandium. atoms of scandium, I meant to say. And then we have one atom of sulfur. And we have 3 plus 3, that gets us 6. So we have 6 atoms of oxygen on the left. Those are our reactants. Now I want to count everything that appears in the product as well. It looks like we have 2 scandiums. We have 3 sulfur atoms. And we have 12 oxygen atoms. So let's go ahead and compare everything. The scandiums are balanced. The sulfur and the oxygen still need to be balanced quite a bit. So I think what I'm going to start with is balancing the oxygen. It might make things a little easier to work with. So I want to make sure that we have 12 oxygens on the left and on the right. We currently have 6. So the tricky thing about this is that oxygen appears in both of our reactants. It'd be really nice if it were only in one of them. That way we would have an easier time modifying the amount. But because we have oxygen appearing in both of these, things are going to get a bit tricky. So we're going to end up having to modify both of our reactants in order to get the same number of oxygen atoms on the same side, on this side as we do on the right side. So we have 3 and we have 3. 3 and 3 make 6. 6 and 6 make 12. So I think what we want to do is double all of these reactants. And I'm going to update the count now. We have 6 oxygens plus 6 oxygens. We get a total of 12 oxygens, 12 oxygen atoms. And now let's take a look at the sulfur. How many sulfurs do we have? Well, we've just doubled the number of sulfurs we have, the number of sulfur atoms. We had 1 before, and now we have 2. So we balanced everything except the sulfur. So we want to kind of be strategic with a way we could possibly do that. So I want to take the LCM of the number of sulfur atoms on the left and the number of sulfur atoms on the right. So in other words, I want the LCM, the least common multiple of 2 and 3. That gets us 6. So that tells me that 6 is the target number of sulfur atoms I want on both sides. So I want to think about what I need to multiply this reactant by, what coefficient to multiply this entire molecule by to get 6 sulfur atoms instead of the 2 that we have right now. So 2 times 3 is 6, which means that I want to take this 2 coefficient that we already have and multiply that by 3 so that we can triple the amount of sulfurs we have on the left. So I'm going to do 2 times 3, getting us a new coefficient of 6. I'm going to do a recount. So the only things that were affected by this were the sulfur and the oxygen. So I'm going to do a recount for both of those. Sulfur, it looks like we now have 6 sulfur atoms on the left. And then I want to count the oxygens on the left as well. So it looks like we have 6 oxygens in the first molecule, and we actually have 18 molecules. Sorry, I can't talk. This has been happening a lot and don't know why. I think it's because I have a major drug problem. I'm highly dependent on coffee. I'm beginning to think I should just have one of those IV drips that continuously pump caffeine in my bloodstream to keep the quality of my videos the way we expect. So I'm sorry about that. I'll do my best. So we have 2 times 3 oxygens in the first molecule, in the first reactant. And then the number of oxygens we have in the second reactant would be 6 times 3. That gets us 18. So we have 18 plus 6. We have 24 oxygens now. And we want to think, what should we do to change the number of oxygens on the left now? So we have 6 of these sulfurs, and we have 24 of these oxygens on the left. So I think what we want to do is we want to double the entire product molecule. So I'm going to put a 2 right there and do a recount. So basically that just doubles everything. We're going to double the number of scandium atoms. We get 4. We have 6 sulfur atoms, and now we have 24 oxygen atoms. Now the only thing left to balance would be the scandium. And it's going to be a bit tricky. We can't really do that without affecting the other things. Well, I just realized that I forgot to include part of the count. So when I doubled this entire first reactant, this entire first molecule, the molecule we have of scandium oxide, I forgot to do a recount for the scandium. We actually have 4 scandium atoms now on the left, which, if I'm not mistaken, completely balances this for us. We're completely finished, but I just want to maybe just do a quick recount and make sure. So we have 4 scandium atoms on the left. We have 4 scandium atoms on the right. Good so far. We have 6 sulfur atoms on the left, and we have 2 times 3. That gets us also 6 sulfur atoms on the right. And now we just have to do the same thing for the oxygen. So we have 2 times 3, so that gets us 6 oxygens, plus an additional 6 plus 3, 6 times 3, 18. So we have 24 oxygens on the left. And then on the right, we have 2 times 4, which is 8, times 3, which is 24. We have 24 oxygens on the right as well. So it's a good thing to do to verify that you actually have balanced it, but we're not completely finished. We want to put this in simplest form. We want to divide all of our coefficients by the GCF of 2 and 6, which would happen just to be 2. So I'm going to divide 2 by 2 and then do the same thing for 6 and the same thing for 2. So we're going to get new coefficients. Instead of 2, 6, 2, it's going to be 1, 3, 1. If it'll let me. One, 3, 1. I hope at least you guys are at least kind of entertained by this, me trying to struggle with Zoom. I hope I'm at least able to provide entertainment value. That's about all I've got going right now for me, to be honest. So we're completely balanced. We're completely simplified. I think we have time to do one more. So we have a fairly complex equation to balance. So this, what we have in front of us, this is a decomposition reaction. Let's talk about what we have in the equation. We have one molecule of ammonium dichromate creating a molecule of chromium 3 oxide, one molecule of dinitrogen, and one water molecule. So just like we've been doing so far, I want to start by making a list of everything we have on both sides of the equation. Always a great place to start. So if we take a look at the hydrogen, this 2 subscript gets distributed to the nitrogen. Did I say hydrogen? I meant to say nitrogen. So we can tell that we have 2 nitrogens to begin with. And we can tell that we have 8 hydrogens. It would help if I could type. Might make things a little bit better and easier for me. We have 2 chromiums. And we have 7 oxygens. I want to do the same thing on the right. We have 2 nitrogens. We have 2 hydrogens. We have 2 chromiums. And we have 3 plus 1. We have 4 oxygen atoms. So just doing a quick comparison, we already have 2 quantities balanced already. The nitrogens and the chromiums are balanced. We have to balance the hydrogens and the oxygens now. So things are kind of tricky even having an odd number of oxygens, especially when it's in just one molecule like this. Things don't generally play nicely when we have odd number subscripts like that, 7. So I think what might be a good step would be to double our entire ammonium dichromate molecule. So because everything is just in one nice, neat package, it's just one single molecule, that the only thing that does is it doubles everything on the left. All right, so now let's see what kind of modifications we have to make to match what we have on the left on the right side. So we have, how many chromiums do we have? We have 4 chromiums and we have 14 oxygens. And things are kind of tricky having oxygen in 2 separate molecules over here on the right side. We want to think about the best possible way to react to that. And I want to save the nitrogens for the very end, just because nitrogen is completely within its own molecule. So we can affect this without affecting anything else. So we definitely want to save nitrogen for the end. Where do we want to go from here is the question. I think I want to balance the chromiums first. So we have 4 on the left, we have 2 on the right. So what I want to do is I just want to double the number of chromiums. And just so happens that we can't double the chromiums without also doubling the oxygens. Whenever they appear in the same molecule, the coefficient automatically affects both of those parts of the molecule. So we're going to double the number of chromiums. We're also going to double the number of oxygens. So we're going to have, this time we're going to have 4 chromiums and we're going to have 8 oxygens. And then we want to think about a way to balance hydrogen next. And it's important to note that if we balance this hydrogen, we're also going to have to rebalance oxygen because we can't affect hydrogen without also affecting oxygen. That's just the way things work. We have 16 hydrogens on the left. We only have 2 on the right. So what I want to do is I want to multiply the entire water molecule on the right side by 8 and then do a recount. So we had 2 hydrogens before. Now we have 16 hydrogens. We had 8 oxygens before. Let's do a recount of our oxygens. So we have, this would be 6 oxygens. This would be 8 oxygens. So we have 6 plus 8, that gets us 14. We have 14 oxygens now. Modify that count if my computer would let me. Sometimes I have to threaten to use my other computer to make this one jealous to start working again. I don't know why, but it works for whatever reason. So let's do a recount. It looks like we have everything balanced except for the nitrogen. And I'm really, really glad I saved that for the end because all we need to do now is slap a 2 in front of the nitrogen. It's really nice because we can do that without affecting any other element, without affecting any of the other molecules. And that's why we want to save it for last. So we have a completely balanced equation now. Sure, it's balanced, but it is not simplified. We have all even coefficients, which means that we can divide by a GCF, a greatest common factor of 2 in all of these. So this 2 is going to turn into 1. Same with this 2. Same with this 2. This coefficient of 8 is going to turn into a 4 after we simplify. All right, perfect. We're balanced. We're simplified. Life is good.